Evaluating limits algebraically. The substitution method that we previously used works for continuous functions. But what happens, how do we evaluate a limit when the function is not continuous at that particular value we're interested in finding the limit at? So I want to take a look at an example that should seem familiar. So I want to evaluate the limit as x approaches 1 of x squared minus 1 over x minus 1. Let's go ahead and take a look at this rational function here. So x squared minus 1 over x minus 1. If I were attempting to graph this, the numerator factors to x minus 1, x plus 1. The denominator is x minus 1, so the x minus 1 linear terms cancel, which means that at 1, the value that makes this linear term 0, there's a hole in the graph. So this is actually the same as the line x plus 1, except not exactly at 1, because at 1 there's a hole in the graph. So this function here represents the graph of x squared minus 1 over x minus 1. So it's the line x plus 1, but right at the x value of 1 there's a hole in the graph. Now, we studied this function earlier, and we used a numerical and graphical approach to determine that this limit actually equals 2. So we can go ahead and look at the graph that's drawn here. As I approach 1 from both sides, I get closer and closer to this y value of 2. But notice that the substitution method, we would try that first, and we would get 0 over 0 because the function is not continuous at 1. So the substitution method only works when the function is continuous. And we can see clearly here that at 1, we have this hole in the graph, so I'm not a continuous function there. So if I were to have tried direct substitution, 1 squared minus 1 over 1 minus 1 is 0 over 0, and this is considered to be undefined. So how do we solve this algebraically without using the numerical and graphical approach? So let's go ahead and take a look at the comparison between the graphs of x squared minus 1 over x minus 1 and x plus 1. So on the left here is x squared minus 1 over x minus 1. So it's the linear function, right? So to remind ourselves, it's the function x plus 1, except at 1 there's a hole. So that's pretty close to just regular x plus 1. So x plus 1 is the linear function, except that it is defined at 1. So there's, a filled-in circle happening here. There's not a hole. So to handle limits of discontinuous functions, like the one above, like this one on the left, what we're going to do is we're going to first use algebra to rewrite the function and then use substitution. So let me remind you again that the limit as x approaches 1 of x squared minus 1 over x minus 1 we concluded was 2. So if you'll notice here the function x plus 1, if I were to have used substitution on x plus 1, so the limit as x approaches 1 of x plus 1, direct substitution, if I plug in 1, 1 plus 1 gives me 2. So instead of evaluating this limit, where direct substitution gives me 0 over 0, I used a little bit of algebra and factored the numerator and canceled those linear terms to get x plus 1, and instead I'll use direct substitution on x plus 1 to get out 2. So we can do this as long as the original function and the rewritten function after algebra, if they agree, if they're the same at all but one point. And at that point, the function has an indeterminate form. So we will formally define the indeterminate forms, but the idea is that this function is almost the same as this function except at 1, and that's the value we're trying to evaluate the limit at. So instead of taking the limit of this discontinuous function at 1, we're going to rewrite the original function using algebra and use direct substitution on the nicer function, right? X plus 1 is a nicer function than this rational one here. So let's formalize these results. Alright, so let's take a look at this theorem, this important result. It says let f of x equal g of x for all x not equal to c in an open interval containing c. All that means is we want to make sure that f and g are the exact same function except at one point, except at c. Well, if the limit as x approaches c of g of x exists, then the limit as x approaches c of f of x is going to exist. and they're going to be the exact same value. Each of those limits will be the same. So instead of taking the limit of f of x, we're going to take the limit of g of x because they're identical functions except at one point. So if they're almost identical everywhere else, they're going to have the exact same limit values. And then to formally define indeterminate, a function f of x has an indeterminate form at x equals c, or f is called indeterminate at c, if when f is evaluated at c. So if when we plug in c, we obtain an expression of the following forms. So if we get out 0 over 0, if we get infinity over infinity, infinity times 0, or infinity minus infinity. And I will tell you that we primarily deal with the first two indeterminate forms. So if when after you plug in the c value, use direct substitution, if you get 0 over 0 or infinity over infinity, then we're going to use algebra to try to rewrite the function and get a different function, some g of x, that we're going to instead take the limit of. So we had a substitution method for limits, but now I'm going to go ahead and extend it. So the substitution method now says that if a function is continuous, then the limit is equal to the function value. So in other words, just go ahead and take the c and plug it into every x, and that's going to give you your answer. So we can evaluate by just plugging in c. But if f of x is indeterminate at c, try using algebra to transform f of x into a new function that coincides with f of x near c, and this new function is going to be continuous so that we can evaluate the limit by applying substitution to the new continuous function that's almost identical to the original one except at one point. So this is just a formal way of saying what we were talking about the entire time. We're going to use algebra. So what type of algebra? We have a lot of types of strategies for algebraic manipulation of limits. So first, the very first thing is always ensure that direct substitution will result in an indeterminate form. So always try to take the c value and substitute it into x, and only if you get 0 over 0 or infinity over infinity, that's when you're going to try to, number one, factor or expand and cancel, or you're going to try to multiply by the conjugate in either the numerator or the denominator, or you're going to try to combine fractions and simplify. So these are the algebraic strategies we are going to use in solving limits if we get an indeterminate form after direct substitution. So now we're going to do one example of each of these types of strategies. Alright, for this first example, we're told to find the limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3. So remember, the very first thing we try on any limit is direct substitution. So I've gone ahead and shown what direct substitution yields for us. So if we were to take negative 3 and substitute it into every x, we would end up with 0 over 0, which is indeterminate. So that's our cue to try something else. So the first strategy that we're going to try is we're going to try to factor. So in the numerator, I have this quadratic function that I'm going to factor, and it's going to factor to x plus 3 times x minus 2. And then in the denominator, I have x plus 3. So notice x plus 3 and x plus 3 are both in the numerator and the denominator, so I can go ahead and cancel those two linear terms. And this is going to become the limit as x approaches negative 3 of x minus 2. So I want to be very clear here that this function and this function are not identical, but they are identical except at one point, at the point x equals negative 3. So the only reason that this line, this first line, is equal to this next line is because of this limit symbol. So off to the right, I'm going to explain what I mean. So here's what you couldn't write. You can't say that x plus 3 times x minus 2 over x plus 3, that equals x minus 2, because these two cancel. So this is not true. But this left side is true. I'm able to write an equal sign here because I wrote the the expression of a limit. So these two are only the same limit values. They're not exactly the same two functions, right? So this is equal to x minus 2 except at x equals -3. But this isn't true unless I put this extra little piece here. So the point I'm trying to make is you have to write limit every single time in order for you to be writing correct work or work that makes sense. So you can't just put equals x minus 2 and forget this limit as x approaches -3 portion, or your work is incorrect. So now, once you take the x value, -3, and use it and substitute it into the x, then the limit symbol can be removed. So I'm about to take this -3 and substitute it into the x value. So it's going to be -3 minus 2. Once you make that substitution, now the limit part goes away. So -3 minus 2 is going to give us a value of -5. So we've gone ahead and done our first example of algebraic manipulation to solve a limit. So we factored and then we canceled the linear terms that were the same, and those two limits are going to have the same value because these two functions are the same except at the value -3. And then we used direct substitution on this nicer function, right? On x minus 2, there was no problem taking -3 and substituting it into x. We got a real answer of -5. We didn't get 0 over 0, right? That's the only problem when we get 0 over 0 or infinity over infinity. So now let's take a look at another example. All right, in this next example, we want to find the limit as h approaches 0 of h plus a squared minus a squared over h, where a is a constant. So I've gone ahead and started using a little bit more variables and a little bit less numbers. So hopefully it's not going to be that much more confusing. I just want to make sure you see first that the limit as h approaches 0 means that when we try direct substitution, we're going to go ahead and replace all of the h's with zeros because a is some number. It's some constant. So direct substitution first. We take the 0 and substitute it everywhere there's an h. So we're going to have 0 plus a squared minus a squared all over 0. So the top is a squared minus a squared. So the same thing minus the same thing gives us 0. So we get 0 over 0, an indeterminate form. Now, we want to try to use algebra here. And the next strategy that we're going to try is to expand. So here, h plus a squared, well, that can be distributed. So this is going to become, and I'm going to show, whoops, quite a bit of work here. H plus a squared is h plus a times h plus a. So just to be clear, the exponent does not distribute to the h and the a. When I say distribute, it means that we're going to need to take h plus a times h plus a. And I can't forget that in the numerator, I still have minus a squared. And in the denominator, I still have h. So let's keep going. I have to continue to write limit every time. So now h plus a times h plus a. So first we're going to do h times h. So we'll have h squared. Then we're going to have h times a. So I have ha. And then I'm going to have a times h. So another plus a times h plus a times a. I'm going to have a squared minus this a squared right here. So just so that we're not lost, let me color code it. This h plus a times h plus a, this first part, corresponds to this whole thing, right? That's expanded out. And then this minus a squared is this portion here. And then we're going to divide the entire thing by h. So now we're ultimately trying to figure out what we can cancel, right? How can we rewrite this? So the minus a squared is going to cancel with the plus a squared. And then here, HA and AH, those are the same things, right? So this is two copies of AH. So this is going to become the limit as h approaches 0 of h squared plus 2AH. So remember, HA, AH, same thing, so I have two copies of that all over h. So what I need to ultimately do is get rid of the h in the denominator. That's causing the problem, because when I use direct substitution, when I take the 0 and plug it into h, I can't have a 0 on the bottom. So in the numerator, both of these terms have an h, so I can go ahead and pull out an h in the numerator. So the top would become h times h plus 2a. So I'm taking an h out of each piece, all over h. And now, because I have things being multiplied, I can cancel the h's. And I'm going to continue my work up here. The limit as h approaches 0 of h plus 2a is all that's left, because those two h's canceled. Well, now there's no problem with taking this 0 and substituting it into this h. So if I do that, and remember, once I take the 0 or take this number and substitute it in, I stop writing limit. So take the 0, I'm going to have 0 plus 2a, which is just 2a. So my final answer here is 2a, right? It involves the variable a, because my original problem had two variables to begin with. But remember, a just stands for some number. So if originally a was 2, the 2 would carry all the way down to the final part of the problem would be 2 times 2, we'd get 4. So we're going to have a lot of problems where we don't just all have numbers, we do have variables. So it's good that you see this type of example early on. Alright, so far we've used factoring, expanding, and now we're going to move on to the strategy called multiplying by the conjugate. So we're trying to find the limit as x approaches 0 of radical x plus 1 minus 1 all over x. So no matter what, we try direct substitution first. We take 0 and substitute it into x. So we're going to get 0 plus 1 under a radical, which is just 1. And then 1 minus 1 is 0. The denominator will just be 0. So we do get our indeterminate form, which tells us keep going, do more work. So the work that we're going to do, multiply by the conjugate. Now, just as a quick reminder, the definition of a conjugate, real fast and informally. If I have two things being added, so a plus b, the conjugate of a plus b is a minus b. And the reason is because when you multiply a plus b and a minus b, you multiply an expression times its conjugate, something nice happens. So I'm going to have a times a, that's a squared, a times negative b, that's minus ab. Then I'll have b times a, so that's plus ab, and then minus b times b, so minus b squared. The middle terms cancel, right? Minus ab plus ab, these cancel, and you get a squared minus b squared. That's the benefit of a number or an expression and its conjugate. So here, the conjugate that we're going to multiply by is going to be the conjugate of the numerator. So whenever you see a radical, that's kind of your indicator that you're going to multiply by a conjugate. So wherever the radical is, in this case it's in the numerator, that is how we're going to decide what to multiply by. So what is the conjugate of the expression that involves the radical? So I have to write the limit as x approaches 0 of radical x plus 1 minus 1 all over x. So what we do is we multiply by radical x plus 1 plus 1. So the conjugate means we change the sign in between the two things being added or subtracted. So in this case, I have square root of x plus 1 minus 1. So that means that the conjugate is changing the minus to a plus. So I can't just change the problem though. So I can't just multiply by radical x plus 1 plus 1. I'm changing the problem. But what I can do is multiply both the numerator and the denominator by radical x plus 1 plus 1. So why can I do that? So what I'm doing is I'm multiplying by this quotient here. But notice, it's the same thing over the same thing. So if I told you what's 3 over 3, same thing over the same thing equals 1. So when I multiply by the same thing over the same thing, I'm not changing the problem, because it's just like multiplying by 1. So that's all I've done here is I've cleverly multiplied by 1. And I'm doing that because when I multiply the numerator right now, well, it's an expression times its conjugate. So something nice is about to happen to the middle terms. So the limit as x approaches 0 So in the numerator, I'm going to have radical x plus 1 times radical x plus 1. So multiplying the first terms together, well, if the same thing is under the square root underneath the radical, the square root symbols are going to cancel. So multiplying these first two, I'm going to end up with just x plus 1. Now, the next thing I'm going to multiply is radical x plus 1 times 1. And then the inside is negative 1 times radical x plus 1. So when I do the outer portions and the two inner portions, they're going to cancel each other out, right? That was the benefit, is the middle terms cancel. So I'm going to end up with negative square root of x plus 1, positive square root of x plus 1. Those will cancel. So the final two terms are multiplying negative 1 and positive 1. So I'm going to have negative 1. So that's what happened when I multiplied the two numerators together. I lost the middle terms. So if you need to convince yourself, you can write it all out, but for this reason, the middle terms cancel. And in the denominator, here's where I want you to maybe make a note for this in your notes, is that you do not need to worry about actually multiplying or distributing the other part of the fraction. So in this case, we multiplied the numerators together because we multiplied the conjugates by each other. But in the denominator, x and square root of x plus 1 are not conjugates of each other. And we don't want to really do anything with these two other than just write them down next to each other. So we are multiplying them, but there's no need to distribute. We do not distribute. It's going to make our life harder. So the denominator is just x times the whole quantity, so I have to make sure it stays in parentheses, radical x plus 1 plus 1. So now, in the numerator, look what happens. I have x plus 1 minus 1. Plus 1 minus 1, that works out nicely. Those two cancel. So what I have left in the numerator is an x, and in the denominator, I have an x that's being multiplied times this expression. So this x and this x will cancel. So in the numerator, what I have left is 1. Please be careful, we do not have 0 left over, we have 1, because what we had is 1 times x. So when we cancel the x's, I have a 1 left in the numerator. So what I have is the limit as x approaches 0 of 1 over radical x plus 1 plus 1. How did this help, you might ask? Well, remember, what are we trying to do? We're trying to use direct substitution and not get an indeterminate form. Well, when I take 0 now and plug it into this x value here. So remember, this is the step where if I am plugging in the number, I don't write limit anymore. So what I'm going to have is 1 over the square root of 0 plus 1 plus 1. So on the top I have 1. I have the square root of 1, which is 1. 1 plus 1 is 2. I end up with 1/2, which is not an indeterminate form, so it is in fact the final answer. So this strategy of multiplying by the conjugate is a bit more work than factoring or expanding, but your indication to use this strategy is when you see a square root and knowing what it means to be the conjugate of a particular expression, whether in the numerator or in the denominator. Alright, in this last example, the strategy we have not yet used is combine and simplify. So in this next example, the limit as x approaches 2 of 1 over x minus 2 minus 4 over x squared minus 4. So we should think combined when we see two separate expressions. So here I have these two rational functions being subtracted, so I can combine them together by finding common denominators. But again, the first thing we try with any limit is we take this number and we substitute it into the expression, use direct substitution. So direct substitution is going to give us, so I'm going to have 1 over 2 minus 2 minus 4 over, so 2 squared is 4, 4 minus 4. So I get 1 over 0 minus 4 over 0. So 1 over 0 and 4 over 0 are actually forms of infinity. So this is an undefined expression when I have a 0 on the bottom, but specifically when I have a number divided by 0, it's considered a form of infinity. So this was one of our indeterminate forms. Comes up a lot less often, but it is still an indeterminate form. So we're going to use some algebra by finding the common denominator, and then we're going to simplify. So I'm going to show all of my steps here. I have 1 over x minus 2. And here, x squared minus 4 hopefully jumps out at you as something that can be factored as a difference of squares. So the denominator is x minus 2, x plus 2. So remember common denominators, what I have to do is if on the right side I have x minus 2, x plus 2, on the left side I want x minus 2, x plus 2. So if I multiply the denominator over here by x plus 2, I also have to multiply the numerator by x plus 2. So the limit as x approaches 2 of x plus 2, so times that 1 is just x plus 2. And now this is x minus 2, x plus 2, minus 4 over x minus 2, x plus 2. So when these have common denominators, right, when fractions have common denominators, we can put them together, which means combining their numerators, and they keep the same denominator. So the limit as x approaches 2 of x minus 2 is in the denominator, or x minus 2, x plus 2. In the numerator, I have x plus 2 minus 4. So what's going to happen in the numerator is I'll have x minus 2. The denominator is x minus 2, x plus 2. And I cannot stop writing limit because I haven't substituted in my number yet, so I keep writing limit every time. Now you'll notice that in the numerator, this whole expression, x minus 2, cancels with the bottom expression, x minus 2. So in the numerator, what we have left is a 1, right? Again, not a 0. I have 1 times x minus 2. So the limit that I have left is the limit as x approaches 2 of 1 over x plus 2. So this is a lot nicer to work with, right? 1 over x plus 2 is much nicer than this original expression here. And in fact, I can go ahead and take my 2 now and substitute it into x to get 1 over 2 plus 2, or 1 over 4. So 1 over 4 is not an indeterminate form, it's a numerical answer, so that is the final answer to my problem. And again, once I substituted in the number, I stop writing the limit symbol, and then box in my final answer. Alright, in this next example, we're asked to find the limit as h approaches 0 of 1 over 3 minus 1 over 3 plus h all over h. So this is slightly different because the variable is h, but that's fine because all of the variables are h. And since we're approaching a numerical value, we can go ahead and try direct substitution, just substituting the 0 into the h's. And direct substitution yields 0 over 0. So the work has been shown. We do get an indeterminate form here. So the algebraic strategy that we're going to use is we're going to combine fractions. So I have 1 over 3 minus 1 over 3 plus h in the numerator. So I can combine those two fractions if I find common denominator between the two, between 3 and 3 plus h. So it's just the least common multiple here, 3 times 3 plus h. So that's going to be the strategy. So we'll go ahead and start our work, and I'll go ahead and make some space. So we have to rewrite the limit as h approaches 0, or L as h approaches 0, and I'm going to have my denominator will be 3 times 3 plus h. So this left one already has a 3, so if I put a 3 plus h on the bottom, I have to put a 3 plus h on the top. And I'm just multiplying that by the 1 that was already there, so I'm just going to go ahead and leave it as 3 plus h, because multiplying by 1 doesn't affect anything. And then minus my second fraction, well, I need that common denominator, 3 times 3 plus h. If the bottom already has 3 plus h, if I multiply the bottom by a 3, I have to multiply the top by a 3. Well, the top was a 1, so it's going to become a 3. 1 times 3 is 3. So now my two top fractions have the same denominator, and this whole thing was all over h. So we can combine the two fractions on the top. So they're going to have the same denominator. We're basically going to be combining their numerators using this subtraction symbol. So we're going to have 3 plus h minus 3. Now keep in mind if there was more than one term over here, so more than just the 3, this negative would distribute to all terms involved. But there's only that one term, so our next line is going to look like the limit as h approaches 0 of 3 plus h minus 3 over 3 times 3 plus h, so the same denominator, I turned it into one fraction, all over h, and I'm going to write it as h over 1, and we'll see why in just a second. So now my 3 plus h minus 3 on the very, very top numerator is going to have the 3 and the minus 3 part cancel. So what I have is h over 3 times 3 plus h, so one fraction, all over another fraction, h over 1. So how we handle compound fractions like this, the limit as h approaches 0, is instead of dividing by a fraction, I multiply by the reciprocal. So h over 3 times 3 plus h, so that's this top fraction, times 1 over h. So the reciprocal of h over 1 is 1 over h, so I multiply by the reciprocal, and you'll notice that now I can cancel the h's because this operation is multiplication. And what I have at this point, I'm going to work to the right because I ran out of space already. The limit as h approaches 0 of 1 over 3 times 3 plus h. So now that I have combined fractions and I've simplified, I can use direct substitution. I can substitute the 0 into the 1 and only h, and I will not get an indeterminate form. So what I will get is 1 over 3 times 3 plus 0. So I'm substituting in the 0 for h, which is 1 over 3 times 3, which is 1 over 9. So 1 over 9 is my answer. I want you to notice a few things, that I dropped the limit as h approaches 0 portion from this step to this step. So once I substituted that 0 into the h, I went ahead and dropped the limit symbol. So that is when you have to drop it, and it has to stay on every other step until that point, and it does have to be removed at that point. And I also never bothered to multiply out 3 and distribute it into 3 plus h. So it was just not necessary. I never had to do that. So we really want to focus on what we were going for, which was combining fractions and simplifying. To simplify means to make it look nicer. It wouldn't look nicer necessarily if I wrote it as 9 plus 3h. So we just left it as 3 times the quantity 3 plus h, and we got out our answer of 1 over 9. In this next example, we're asked to find the limit as x approaches 0 of e to the 3x minus e to the x over e to the x minus 1. So we're dealing with a different class of functions. We're dealing with exponentials, but it doesn't matter. We still try direct substitution. We plug the 0 into all the x's and see what happens. Well, anything to the 0 is 1, so we end up with 1 minus 1 over 1 minus 1. We end up with 0 over 0. So when we get indeterminate, it means we're going to do more work. So one of the things that a student actually showed me that I really like to help us remember that 0 over 0 means more work is they wrote it as oh no. So oh no, indeterminate means that we have to do more work here. So the more work that we're going to do on this problem, although it may not be obvious, is the strategy of factoring. So in the numerator here, I can factor out an e to the x. So we're going to have the limit as x approaches 0 of e to the x times the quantity. So if I take out one copy of e to the x here, I'm going to have e to the 2x left, minus a 1, because I pulled out the only copy of e to the x that was right here. So I'm going to have just the minus 1 left, and then all over e to the x minus 1. So the strategy is factor and then cancel. So at this point, nothing can be canceled. So e to the x minus 1 in the denominator is like one whole thing. So I don't have anything that I can cancel. E to the x and this e to the x do not cancel. It would have to be an e to the x minus 1, or just a regular e to the x down here on the bottom being multiplied by this whole quantity. So I can't cancel anything yet. But I can factor more. So e to the 2x is e to the x quantity squared. So what I really have here is a difference of squares. So I have e to the x squared minus 1 squared. So this is going to factor, I'm going to make some more space here. This is going to factor to, so the limit as x approaches 0, the e to the x in the front still stays there. It's going to factor to e to the x minus 1 e to the x plus 1. So again, that was because this piece right here is the difference of squares. So a squared minus b squared factors to a minus b, a plus b. It's just not super obvious because this is exponentials that we're talking about here. But hopefully now that you see that that was able to be factored, now we can cancel the whole quantity e to the x minus 1. So that whole term and that whole term, or that whole expression, cancels. So let's see what we have left, if what we have left is not going to give us any problems. So we have the limit as x approaches 0. Well, all we have left is e to the x times the quantity e to the x plus 1. And if I substitute in zeros into these x's, again, since I'm about to substitute, we're going to drop the limit part. So I'm going to get e to the 0 times e to the 0 plus 1. So anything to the 0 is 1. So I have 1 times 1 plus 1, which is 1 times 2, which is 2. So this limit worked out to be positive 2. So one of the things that students find hard about calculus is actually the algebra component of it. So a lot of these strategies have to deal with fractions. They've had to deal with exponentials, factoring, the difference of squares. So I'm now going to show you a little pie chart. So this pie chart is kind of meant to be a joke. It's the sources of error in calculus. So most people get the arithmetic and the algebra part wrong. We haven't gotten there yet, but I will show you this pie chart again later when we hit the chain rule. That is another big mistake in calculus that is actually calculus, and then integration later. But right now, we can maybe kind of see that calculus is a struggle because your arithmetic and your algebra skills need to be brushed up on. So in summary, let's go over what happens if we're trying to evaluate a limit with direct substitution. So if direct substitution results in a number, the limit is that number. So if you substitute in the number, you get out a number, that's it, that's your answer. If direct substitution results in 0 over some non-zero number, so here a cannot be 0, then the limit is 0. So that's just remembering that 0 over some number is 0. If direct substitution results in some non-zero number over 0, then the limit does not exist. So we have an infinite limit, and what we really have here is we have a vertical asymptote happening. Because vertical asymptotes correspond to infinite limits. So that's when we have a number over 0. And then if direct substitution results in 0 over 0, well, that's indeterminate. Remember, oh no, we have to do more work. And the answer is not, does not exist. So when we get 0 over 0, we have indeterminate form. We have to try something like factoring, multiplying by the conjugate. We'll have another strategy later, but so far those are the strategies we have, and we have to do more work.